we'll now look at several different properties of our matrix inverse. Our first theorem says that if we have an n by n matrix, A, and if B is also an n by n matrix, such that either AB is the identity or BA is the identity, then B is the inverse. So we only need to check one of these rather than both. And we'll prove this. So we're going to start by supposing BA is equal to the identity. We'll actually consider the system AX equal to 0. We can multiply both sides by B to get BAX is equal to B times 0. We know that BA is equal to the identity. So on the left of this, we have X, and on the right we have 0. Therefore, since this has only the trivial solution, we know that A is invertible. We can then take BA equal to I and multiply by A on the left and A inverse on the right. On the left, we then have an AB if I cancel the A and A inverse, and on the right I have the identity. Therefore, we also have that AB is equal to the identity. Our next theorem. If we have two n by n matrices, and we know that their product is invertible, then each of our original matrices are also invertible. For this, we're going to start by letting C be equal to B times AB inverse, and we'll define D to be equal to AB inverse times A. In this case, A times C would be AB times AB inverse, which we know is the identity. In addition, DB would be AB inverse times A times B, which is once again equal to the identity. And by my last theorem, we know that this means they each have an inverse. Therefore, we can say that C is A inverse and D is B inverse. Our next theorem. If we have two n by n invertible matrices A and B, then the inverse of their product is B inverse A inverse. So we do have to switch the order whenever we try to distribute an inverse over a product. One way to think of this is if you get up and you get dressed in the morning, you start by putting on your socks, and then you put on your shoes. However, if you want to undo this, we want to take the inverse and take it off, we would start by taking off our shoes and then taking off our socks. So we have to switch the order. And we will prove this by multiplying AB times what we're claiming to be the inverse. Well, moving parentheses around then gives me A, B, B inverse times A inverse. We know this center is the identity, so that leaves me with A inverse, which we also know is the identity. Since I multiplied them and I got the identity, they are inverses. Here, we'll let A be an invertible matrix and n be any non-negative integer. Then we have a few different properties. The first, A inverse inverse, is equal to A. So not only is the inverse invertible, but it's equal to A. In addition, AN inverse is equal to A inverse to the nth power. So if we take a power of an invertible matrix, it's still invertible. The third one, if I try to multiply R times A, that's still invertible. And if I take the inverse, it is 1 over R times A inverse. And then the final one, if I have the transpose, it is also invertible. And it's the same thing as the transpose of the inverse. We'll end with the beginning of the invertible matrix theorem. It is longer than I'm giving here, but that's just because we need a few more definitions, and those will be given in later videos, where we'll also add on. So the invertible matrix theorem is a list of things that are all equivalent, which means if you have a matrix A, either all of these are true or all are false. The first just says that A is invertible. The next, A is going to be row equivalent to I, which means if we reduce, we get to the identity matrix. Next, we say that A has n pivot positions, where n is the size of A. A should be an n by n matrix. The fourth one, the system AX equal to 0 has only the trivial solution. Part 5, the system AX equal to B has at least one solution no matter what vector I pick for B. So this will always have at least one solution. Part 6, there is an n by n matrix C such that C times A is the identity. For 7, similar to 6, this time there's a matrix D such that AD is equal to the identity. And then the very last part, A transpose is also invertible.